All right. Thanks a lot for the introduction, John. So today, indeed, I'm going to talk about the most recent updates that we did in Scala.meta. This is the work that I started at the PFL while I still was a PhD student there, and I continued it at Twitter, my current employer. So what is Scala.meta? Just a really quick recap for those of you who maybe don't know the details. Well, first of all, Scala.meta is cutting-edge research in metaprogramming. So here we can see a screenshot of my PhD dissertation. I'll be defending it next Monday in Lausanne. But it's not just a PhD dissertation, not just theory for the sake of theory. It's actually a promising technology that's used, first planned to be used at the PFL to implement the next generation of macros. So Martin Odersky, during his Scala Days talks in New York and Berlin last year, he said that old macros, they're going away, but we're planning to implement a new macro system based on Scala.meta, the new metaprogramming API for Scala. Also, Scala.meta is used at Twitter, where I work at the moment, and there we build next generation code analysis tools that are based on the old syntactic API and the new semantic API that I'll be presenting today. And finally, Scala.meta is also used at Scala Center. Later today at 5 p.m., Olaf, my former colleague from EPFL, he will present his progress with the Scala fix that's based on Scala.meta and our recent update with the semantic API. Also, Scala.meta is just an open source project. We have a vibrant community. We have lots of discussion on Gitter. We have quite a lot of pull requests, and we have a whole team of maintainers. So if you're willing to get involved, if you get this idea by the end of the talk, you're always welcome. Now let's get to the technical part of the talk. Scala.meta APIs. So how does this metaprogramming library look like? Well, I like to broadly categorize our APIs into two big groups. First, we will briefly discuss syntactic APIs that I've presented over the last year. Well, this is a complete example of some of the APIs that I've been referring to. First, we just do a blanket import, scala.meta._, and this brings the relevant functionality in scope. So for instance, in the second line of the REPL printout, we can see that we take a string, then parse it as a term, and then obtain the parsed result. So the result will be an abstract syntax tree, something that the concept that Matthias has introduced during the previous talk. And with the syntactic API, we can view its structure, which is the next line in the printout. So we can see an application of a name print line to some argument. And also, which is quite a big innovation in Scala.meta, we can also inspect its tokens. So Scala.meta trees not only provide you ways to take a look at their structure, but you can also see all the syntactic details, everything that the tree was parsed from, including white space, comments, these things that were missing in the Scala refactoring talk before. So that's what we've shipped with Scala.meta 1.0, and the current version is 1.6, so this API is pretty much stable. It's been used quite successfully in next generation dev tools, for instance in the Scala FMT project, also created by Olaf. But today's talk is going to be about something different, semantic API. So we have the structure of the code. For instance, we can see that this print line application, it consists of a term apply, a term name, another term apply, and so on and so forth. But what's the meaning behind these trees? How do we figure this out? Again, I like to categorize semantic APIs into three big groups. The first group, it helps us answer the question, what does a given name resolve to? So in the previous example, we saw print line and list. So what do these guys mean? Well, since we know the Scala standard library, we can immediately answer the question. So print line is defined in pre-def, and list is just a type alias in the Scala package. But for more involved programs, that's a much more complicated question. And this is something that DevTools would like to know the answer to. The second big question is what's the type of a given expression? So here on this slide we have 7 different expressions, and they have quite various types. So for instance, literals 1, 2, and 3, they are typed as ints. The application of list to those ints is, well, naturally list, and so on and so forth. So this is also a very important question that we need to answer. For instance, to do refactorings or to do other automated processing of Scala code. And finally, this is a concept that's very important to Scala, also briefly covered in the previous talk, the sugarings. So the Scala specification, it defines that some of the language constructs, they get desugared by the compiler, that is transformed into a different form. That's not written in the sources, but that's derived by the compiler intermediately while it processes the program and transforms it into bytecode. So here we can see that this list thing, it's actually a reference to a companion object of a list. And the application of this companion object to its arguments means invocation of the method called apply. And then, recursively, this invocation of the apply method, it also implies type inference, which appends the int type argument. So these rules, they're pretty involved, and we definitely need a comprehensive API to access the sugarings. Or so we thought. So anyway, the work on the semantic API has been going on for about 2 years, I would say. And what we figured out during this research is that the 3 fundamental questions that I posed on the previous slides, they can be very easily answered using compiler internals. So we have the Scala Reflect metaprogramming library that uses the internals of the Scala compiler. And all of that and much, much more, it can be done with Scala Reflect. But unfortunately, in order to do this robustly, so Matthias touched this subject a little bit during the previous talk. And more importantly, in order to do this portably, that is to write metaprograms that can execute in IntelliJ or in Dotty, the new upcoming Scala compiler, it's very, very hard. Well, unfortunately, it turns out that a comprehensive solution to the portability problem and the robustness problem, it takes a huge time to implement. So I personally spent about a year of my life trying to do that. And well, that's quite a lot of time. And what's the most depressing fact that I found out during my research is that, well, it takes me a year to implement that, which means that if the new version of Scala comes out, for instance, Dotty, well, will it take us another year to implement this functionality for Dotty? Well, if it does, then it's super depressing. However, I wouldn't be doing this talk if I haven't found, well, a new hope, like Matthias said previously. So this definitely made us rethink our strategy. So previously, we were looking for a comprehensive solution that answers all of the 3 questions immediately and works in all versions of Scala, in all compilers, including IntelliJ, so on and so forth. Well, it turns out that it really takes a lot of time to implement that. So let's ship this incrementally. I mean, it's a pretty obvious idea, but that's something that had to be done. And secondly, the fact that we figured out, well, maybe we don't need a 100% solution. Maybe a 95% solution that can be implemented in 20% of the time is actually really good. And that's what we need to start with. So, well, basic engineering technologies, but they were really important in applying to our project. And finally, there's some line that we're not willing to cross. So portability, that is the ability for metaprograms to execute on different versions of the compiler or in the IDEs like IntelliJ. This is essential, and we're just not going to give this up. The whole Scala.meta project, it was started with the desire to have macros that run equally well in ScalaC, in Dotty, and in IntelliJ. So this is something that's been with us from the day one, and this is something that we will not sacrifice. And now, let's just discuss one of the 3 questions that we've seen before. How do we give meanings to names? So in this quasi-quote print line of list of 1 to 3, this example will follow us through the entire talk. How do we figure out what print line and list mean? The other questions, we'll answer them later. Well, after all, I will need to give more talks later in other conferences. All right. let's get acquainted with the new technology that we've come up with to solve this naming problem, something called semantic databases. So without going into definitions and stuff, let me just give a real quick example. So here we have the Finagle project, something that was created at Twitter, that I compiled with our compiler plugin in order to produce a semantic database. So you can see this semantic DB file, which contains some information about the source code that has been compiled. It's located next to class files that were produced by SBT, in that case for the Finagle core subproject of Finagle. So as you can see, this is a pretty sizable file. It's about 5 megabytes. That's because the current encoding of semantic information that's contained in these source files, we just use textual encoding. In the future, we'll probably migrate to Thrift or something like that. But, well, at the moment, it's implemented like this. And so this is some information about Scala programs that can be packaged in jars. So that's why we put it into the target directory of SBT. And that can be distributed on Maven if you want to do that. Why would you want to do that? Well, let's see a very quick example. Let's start with a simple file called library.scala. Well, you can see our favorite print line of list of 1 to 3 wrapped in the main method. And let's compile it with the Scala host compiler plugin, which is a new part of the Scala.meta platform, starting from version 1.6. So we provide this compiler plugin on the command line, or there's an SBT plugin that does this for you automatically. There is a tutorial about that. And afterwards, after compilation, we see not only the class files that are produced and that are visualized with ls, but also the semantic DB file. So now I won't tease you anymore, and let's just see what's there in that file. So as I promised, in textual format, we see some metadata about the program. And in particular, in the current version of the semantic database, for every compilation unit that was passed to the Scala compiler, for every name in that compilation unit, we save unique identifiers that roughly correspond to fully qualified names. So for instance, we had this object called library, which was in the empty package, an unnamed package. So here's the fully qualified name, empty.library. Also, we have this main method, which is signified by library.main plus the signature. That's because in the Scala language specification, methods, overloaded methods, they're distinguished between each other using JVM signatures. So if you go down and down the file, you can see that all the names in the original program, they have been resolved, including the print line, something that we've been trying to give meaning to. So it's Scala predef print line plus the signature, as I promised, and list, which points to list.apply. That is, it takes the sugarings into account. So how can we use this semantic database? Well, one of the cool things about semantic databases is that they're portable. So unlike similar technologies that were explored before, semantic databases, they're not tied to a concrete implementation of a Scala compiler. So as you've seen, it says just some sort of textual file, or in the future it will be a binary equivalent thereof. And it does not refer to any symbol tables. It does not refer to any types or compiler phases, nothing like that. So whatever is in the file, that's it. And as a result, a semantic database, it can be loaded and deserialized in any environment, which I find to be pretty neat. So you don't need the, yes, please.
I've noticed that these are the bytecode fully qualified names. So it's all erased. Are you saving any of the Scala information?
That's a very good question, so I'll repeat it. What Sam wants to know is whether we're saving additional information, because what seems to be here in the semantic database file is a bytecode name that corresponds to the JVM representation of symbols. Well, at the moment, we're using bytecode names just because this is how Scala language specification defines definitions and uniqueness of names. But in the future, and I will talk about this in future work, we plan to save more information. And actually, your feedback is instrumental here, because this is just the first release of the semantic DB technology, and well, we need feedback to accommodate more information. It should be pretty easy to store additional metadata. All right, there's more questions.
Let's say if you go to companion base class, there is a class and companion class generated for that one. And it should point to the same space in Scala code because it should point to where the case class is generated, class is defined. It will support that or like?
Okay. So I think the question was about distinguishing classes and objects with the same name, because Scala programs have two namespaces that don't coincide, terms and types. Well, actually here, I said that the strings to the right at the right-hand side of arrows, they are like fully qualified names, but they're a bit more, because as you can see, the strings end with either a dot or a hash. So this is our notation to say if it's a dot, if it ends with a dot, then it's a term. If it ends with a hash, like Scala array or Scala predef string, then it's a type. Most likely a class, but maybe a reference to a type member or something like that. So that's the long answer, and the short answer is yes, it's possible to distinguish classes and companion objects. All right, Julian, please go ahead.
How would you represent the type member that doesn't have a JVM equivalent? Is it the upper bound? Or?
All right, so great question. So what do we do with type members that are erased on the JVM? Well, actually, we only use erasures and signatures of methods. That's because this is how you distinguish overloaded methods according to Scala language specification. Everywhere else, we don't use, we are not tied to the JVM. So type members, they're going to be represented as their names, fully qualified names. So here in this example, just one clarification, maybe that'll answer another question. So here we have fully qualified names for everything. But actually, for local variables, you cannot have fully qualified names. And for those guys, we have a URL that points to a file where the member is the local variable is defined plus an offset. So the main point here is we need to define a unique ID of a symbol. So we need to represent this definition somehow. And the exact representation is not that important. All right?
Just another simple question. What if you wanted a semantic database for some code I'm currently actively working on? So that's like a change.
All right. So the question here is about whether a semantic DB can be generated interactively. Yeah. Because we've seen in this use case, we generated it in batch mode. So we have a program, we compile it, and voila. Well, theoretically, I think a semantic DB could be generated interactively, but that's a non-goal at the moment. So we are focused on supporting batch mode first. Then we will probably go to macros, which involve synthetic code, and then probably to interactive use cases. But if any of you guys want to contribute, it should be possible. It should be possible. All right. I'm really happy that we had so many questions. Let's just briefly sum up the semantic DB thing. So one cool thing about semantic databases is that they're portable, which means that we can finally write developer tools outside the context of the Scala compiler or of a different host. Because currently, a lot of tools, they are written as compiler plugins. They run within the context of Scala C, and as a result, they have access to the symbol table of the compiler, to all the subtyping logic, and whatever else is implemented there in Scala C. Unfortunately, this tightly couples them with a particular version of the compiler. And the semantic database is an attempt, well, which was the core part of the Scala.meta vision, to make Scala.meta programs portable. And I think this will be a really, really interesting opportunity to explore what new things we can do with developer tools. Also, as we've seen, semantic data, you can persist semantic databases, which means that you can also distribute them using regular means, for instance, via Maven. And as a result, it is conceivable to think that this info will be available on demand. And just as currently, we can inspect metadata of running programs using Java reflection, we will also be able to obtain additional information using Scala reflection that's powered by semantic databases. And finally, since semantic databases, they can be easily merged together, they contain information about compilation units that are supposed to be independent. We can imagine them to be generated in a distributed fashion and then merged using for instance, the MapReduce technique. All right?
So
please.
I could be using these semantic databases to type level without using actual version numbers at all?
Well, yes, sure. It is possible to use semantic DBs to do reflection. So for instance, to compare APIs. OK. So now we know all about semantic DBs, well, at least all the high-level information. And let's proceed to how we expose them to the users. So in order to implement the Scala.meta semantic API, we have introduced the concept of a mirror in Scala.meta 1.6. And the mirror is something that is very, very simple at the moment. As I said, we plan to start really small and then continuously expand the API. So currently, it only contains 4 methods. The first 2, they're really simple. First, we have a dialect, which corresponds to a version of Scala, for instance, Scala 2.11, .c, SBT 0.13.6, or something like that. Then we have sources, which basically correspond to the domain that we're reflecting, to a list of compilation units. And the last 2 methods, they're something interesting. First of all, we have this semantic database that's exposed via an object model so that you don't have to parse these text files or binary files yourself. And then we have a high-level method that resolves a given reference into a symbol. So this implementation is very simple. It does not require Scala compiler running. It just requires a semantic DB. So basically, it looks up a location in the database, and if it exists, it returns the result. Also, here we can see a very, very simple example of how you use a mirror to do semantic APIs. So first of all, Scala.meta 1.6, it provides 3 ways to create a mirror. We'll go through them on the next slide. But in this example, we can instantiate a mirror from a class path. So remember, class path, target directory, it contains semantic DB files. So this is where we're going to load them from. And we also get the source path, because semantic databases, they refer to source files. So we need them to resolve information. So first of all, once we have a mirror, we can obtain the database and maybe do some low-level stuff with it. That's the first layer of the semantic API. And secondly, here's the high-level layer. So we can traverse the sources that are listed in the semantic database, and we can resolve names there. So in the last 6 lines of code, in this small snippet, we go through all the sources, we look up all identifiers that are called print line, and then we figure out what these identifiers mean. All right, so as I promised, we have already implemented 3 ways to obtain semantic databases. First, from a running compiler, if you need to run inside the context of Scala C. Then you can create what we call an offline mirror, which does not require Scala C, which just loads semantic DB files from class path. And finally, we have implemented a shortcut that can easily create mirrors from SBT builds, if you create builds in a special way. So in the example provided here, under our GitHub organization, you can take a look how it's all done, with comments and explanations. All right, so since it's a dedicated DevTools conference, I figured that it would be important to share implementation details, how we did this semantic API project. Because as I said, this was a research project which started with a series of failures. And that was so much fun, so I'm going to share this with you so that you have fun as well. I did. Well, what were the main challenges that we encountered during this project? Well, you see, Scala's type checker is really, really complicated. So it has tens of thousands of lines of code. And re-implementing it from scratch, it's really hard. So we just have to use what we have, for instance, in Scala C or in IntelliJ. And the problem with those implementations is that attributed trees, that is, trees that contain symbols and types, they're actually platform dependent, which means that Scala C has one idea about what the type of a given complex expression is, and IntelliJ maybe has a different idea. And since it's all undocumented, type inference, desugarings, no one knows who's right. So basically, that's the deal, and that's the environment that we have to operate in. Well, our first attempt to somehow unify this and make this a bit robust started in 2015. So we had the delusion that we can take compiler ASTs from the Scala compiler, then somehow revert this undocumented desugarings that were done by Scala C, and then convert the ASTs, plus these reversions into Scala.meta ASTs. It took me half a year to pull this off, and that was several thousand lines of code. A lot of work, really. I had to hack the type checker, so there's a technique to replace a running type checker from within the compiler plugin. Fun stuff. And well, using all this heavy artillery, we almost got this working. But then I figured that if it took me so much to write initially, then it'll take me as much time and even more to maintain. So, well, I decided to scrap all that. That was pretty sad, but that's well, a natural outcome. In 2016, we tried another strategy. It was fun as well. So we took abstract syntax trees from the Scala compiler, the ASTs after typer, and then we also took Scala.meta ASTs that we parsed from the same source file. So for a source file, we had two representations, two views of that source file. First, whatever ScalaC thinks of it, and second, whatever Scala.meta thinks of it. And then we tried to reconcile it. So the benefit here would be that we wouldn't have to undo these desugarings that I was referring to, because we just traverse these two ASTs together, and it's all fine, right? Well, that was a very good scientific hypothesis. It was very brave and courageous. I wasted several more months on that. The good thing about this approach is that it indeed did not require any modifications to the type checker, but the bad thing is that it didn't work. After writing several more thousand lines of code, I decided that, nah, that's not good. And I even pulled Olaf from the Scala Center into this thing. He also worked on that. So we had fun together. At least I wasn't alone. That was some progress. And finally, at the end of the year, someone around the Scala Exchange conference, we had a different idea, something that Martin Odersky proposed a while ago. So here's another take on the semantic API. And this is the one that I believe will work. Or otherwise, well, I'll give another talk here in a year. So the deal here is that, again, we start with compiler ASTs because that's the best that we have. And then for every name in that AST, for every name in the compilation unit, we use positions to obtain a corresponding AST in the compiler. So naturally, the compiler ASTs, after type checking, they're desugared, they're really screwed up, but we don't care. We just use positions and hope for the best. And then, for every AST that we located, we figure out its symbol. So as Matthias mentioned in his presentation earlier, every tree has a symbol. So we just look there and again hope for the best. It might sound really, really reckless, but that's essentially what Scala IDE does for your code. When you command click on an identifier, it does exactly what I said, and it also hopes for the best, and somehow it worked for the guys. So we hope that it will work for us, or, well, we will make it work. And as you can see in this approach, we don't involve any platform-independent ASTs, no Scala.meta ASTs, no AST conversion. So previously, a significant chunk of the complications, it was because we had to convert compiler ASTs into our ASTs. Just transform data structures into data structures. That's hard, and we avoid this completely here. So it took me about a month of work to prototype this and then to release this in Scala.meta 1.6. But what's good about this, just a little bit, and I'll take your question. What's good about this is that the implementation is several hundred lines of code. It is still littered by crazy stuff like look up this thing at an offset +7 or -2, but well, that's what you have to do when you interface with ScalaC. But it's still several hundreds lines of code, not thousands. So, I mean, I have high hopes that it's actually maintainable. All right, please go ahead with the question.
Just a question to that. For every name bullet, I mean, this name is taken from AST or taken from the source code?
Very good question. OK. So actually, we parse the source code with Scala.meta, and then we obtain all the names from the Scala.meta tree. And then we use these positions of those names in order to do queries to the presentation compiler.
OK, so I'm not using Scala.meta. Unfortunately, it's syntactic API, but there's also information about implicits, for example, which are applied.
Very good question again. So implicits, what do we do about them? Well, a good thing about implicits is that they're not written in the source code, implicit arguments, which means that, well, we don't see them and they're not in the semantic database. That's of course a lazy answer. Well, a complete answer, let's go a few slides back. So as I mentioned before, here's the third fundamental question for the semantic API. What does an expression desugar to? And this also involves implicits, because, well, a full application of a method with implicit arguments is a desugared version typically. So that's another question, and as I said, in this talk, we're only gonna discuss this part. That's nice. If you restrict the scope of stuff, then it's much easier to deliver anything. Well, I really, really appreciated that. Only a month of work, and we have something nice. Anyway, so this concludes our brief excursion into the past, and let's proceed to future work. Well, first of all, using semantic databases, even in their current form, which only contain resolved names and no desugarings, no types, it's already possible to do cool stuff. So ScalaFix, and Olaf will talk about this at 5 p.m., ScalaFix can implement new kinds of refactorings, like renames, for instance, using already existing technologies. We can also imagine that with semantic database, we can build code browsers that work not based on grep, but actually use resolved names in order to provide intelligent hyperlinking. We can also imagine how this could improve code reviews tools and so on and so forth. And most importantly, this is where the Scala.meta project started from. We can use the semantic database if we can build it on the fly from synthetic code. We can use it to write def macros. Because currently Scala.meta can only be used to write macro annotations using this syntactic API. And the semantic API is cornerstone to def macros. So that's the first big direction of research. The second direction is, of course, improving the semantic API. As I mentioned, currently we only implement ref.symbol, which is basically resolve a name and give me a pointer to a definition. But of course, semantic APIs are much more than that. So we need to obtain type signatures from symbols, we need to load members of symbols, and a lot of other things. Well, of course, we're not going to deliver this immediately, but slowly and steadily, we plan to implement all of those things that are mentioned on the slide. If you're interested in the roadmap, please go ahead and inspect this issue 604. There's a lot of detailed information there. And if you feel strongly about something, please leave your comments. Really, really appreciate it because we're still in the early design phase. And finally, as prompted by Sam and by some others, we plan to provide more information in semantic databases. This starts with types for all expressions. This is something really important, something we cannot do without. Maybe desugarings. We will see how it goes. We will see how big a demand is for desugarings like implicit arguments and other things. Because that's something that's very hard to implement. And if the demand is not so big, then, well, maybe it's just not worth it. And finally, that's from the discussions with Olaf. Maybe we want to persist tool-specific information. For instance, ScalaFix, it needs to know which imports are unused in source files. So maybe we can just collect this information. It's kind of weird. It's very, very narrow. The domain is very narrow, but why not? Why not put this info? It's well, we're not going to suffer from that. All right. So just to sum up the presentation, we've seen that the new version of Scala.meta that has been released just a couple of weeks ago, it comes with the first with V1 of the semantic API, and currently the semantic API it only includes one method, one high-level method, plus the whole semantic DB stuff. In this year, we plan to ship more and more of the semantic API so that we can implement macros and other intelligent developer tools. Finally, doing all this effort, it uncovered the whole new possibility with semantic databases. So we hope that this concept, it will provide ways to write tools that have not been possible before. We will report about that later during the Scala Days talk that I've been referring to previously. But at the moment, let's keep it a secret. So finally, as I said, this is a very, very early project. And we do need contributions here. And the most important area is testing. So currently we have a compiler plugin, the Scala host plugin that I mentioned before. If you compile your projects, your SBT projects, whatever really, with this compiler plugin, then it will generate a semantic DB file, allegedly. We have tested the compiler plugin on biggish projects. For instance, I mentioned Finagle from Twitter, but we do need more testing. And as the example hyperlink here shows, it's as easy as specifying an SBT plugin in your configuration. So if you would be willing to contribute, that's a really easy and well, good way to help our project. And if you're interested in learning more about the details, just you can visit our Gitter. It's pretty lively. You can find me tomorrow at a given time slot. So there will be discussion tables arranged by the conference organizers. And I'll be at my table at 12. And also we will be doing a hackathon again tomorrow at 17. So a lot of opportunities to contact. So if you're interested, I will be available the whole 2 days. And finally, as I mentioned, in both Chicago and Copenhagen, myself and my colleague Stu Hood from Twitter, we will be presenting how we're using semantic databases and other parts of the semantic API to build tools internally in our company. Thanks a lot, guys, and please ask questions.
So when you want to, for us to use that in tooling, the first, most important thing I need to ask is how fast is this?
Yeah, sure. That's a very good question. I don't have many benchmarks, but this Finagle thing that I've been referring to, generation of a semantic database, it slowed down the compilation by 30%. Of course, this is just an anecdotal benchmark. I didn't do, any warm-ups or stuff, but it shows that it's not 10x slowdown, which would be unacceptable. And also, I have an idea how to parallelize generation of a semantic database. For instance, parsing of Scala.meta parsing of source files, and saving semantic information. I think the overhead could be negligible. At the moment, it's not the focus of the project. We just need to get, features running. But I do believe that it will be OK. All right. Any other questions, guys? Cool. Then find me later. Thanks a lot for attending.